A crate of weight Fg is pushed by a force P on a horizontal floor as shown in figure P5.45. The coefficient of static friction is μs, and P is directed at angle theta below the horizontal. A. Show that the minimum value of P that will move the crate is given by P equals μs Fg secant theta over 1 minus μs tan theta. The goal of this experiment is to identify the minimum value of the force P that makes the crate move. This is a particle model because we can model the crate as a particle in our free body diagram. To get the desired result, we have to sum the vertical and horizontal forces separately, using the equation net force equals the sum of all of the other forces. The net force should equal 0 if the crate is not moving. At the threshold, static friction and the net force will be 0 because the moment before the crate moves, it is in equilibrium, so we set the net force equal to 0. As applied force P increases, static friction increases until it reaches its limit, static friction max, where motion then occurs as shown in the graph. Fs, static friction, is less than equal to μs times the normal force, but at the threshold, the static friction is at its maximum. So static friction max equals μs times the normal force. So we can substitute this into our equation for friction. This equation would be P cosine theta minus static friction, because P cosine theta is the horizontal component of the P force. The net force in the y direction is normal force N minus P sine theta minus Fg, because the normal force N and the force due to gravity Fg are opposite forces in the y direction, and P sine theta is the y component of the P force. Now we must solve for the normal force in the F net y equation so that we can plug it into our F net x equation. Now we can solve for P. We find the equation that matches the books by factoring out cosine theta and dividing both the top and bottom by cosine theta. This problem relates to problem 5.34 from homework 5. In problem 5.34, we calculated the magnitudes of P that would make the block stay stationary, and what would happen if P was bigger or smaller. In part A of this problem, we are analyzing the minimum value of P that would move the object instead of the magnitudes that would keep the block stationary. For part B, the goal is to find the condition on theta in terms of μs that makes motion impossible for the crate no matter the value of P. Intuitively, we can see that if theta is 90 degrees, P is vertical, the crate will not move no matter how large P is. In this part, we are solving to see what values of theta make motion impossible. In order for the crate to be in motion, the x component of P must be greater than or equal to max of static friction. In equation form, P times quantity cosine theta minus μs sine theta, end parenthesis, is greater than equal to μs Fg. μs and Fg are both positive, therefore cosine theta minus μs sine theta must be greater than 0. This means that for motion to be impossible, the value will be less than 0. Now we have to solve for theta. The part of 5.34 that asks how angles relate to the movement of the block relates to part B of 5.45, because they are both talking about the angle of P to the block. 5.45 differs in that it gives the effect of theta on the movement of the crate and asks for the value of theta, whereas 5.34 gives a value for theta and asks for the effect on the movement of the block. 5.34 gives us two values of theta. We see how for the first theta it is possible for the block to slide up the wall, depending on the magnitude of P, while for the second theta, motion up the wall is impossible because the vertical component of P is so small. In problem 5.45, the angle of theta that makes movement impossible would have to be a greater angle from the horizontal axis, so that the horizontal component of P is too small to allow movement.